Paul Atreides looks up at two suns setting over Arrakis. That shot from Dune isn't just visual poetry, it's a claim about physics. And for most of astronomy's history, that claim was considered impossible. Two stars orbiting each other should gravitationally shred any planet foolish enough to form between them. The math was brutal: competing pulls, chaotic resonances, orbital instabilities. Arrakis, by every calculation, astronomers ran for decades, should have been flung into interstellar space or swallowed by one of its suns millions of years before any sandworm could evolve. Then, in September 2011, NASA's Kepler telescope found Kepler 16b, a planet, orbiting two stars, peacefully. The discovery didn't just validate science fiction, it forced physicists to confront a basic question they thought they'd answered. How do planets survive gravitational chaos? Arrakis orbits two stars in a configuration astronomers call a circumbinary system. Both suns orbit each other tightly, while the planet traces a wider path around the pair. Think of two dancers spinning at the center of a ballroom, while a third person walks slow circles around them both. For this arrangement to last billions of years, the outer orbit must stay far enough from the inner dance. Too close, and gravitational tugs become erratic. The planet's path stops being predictable. Here's where the physics gets uncomfortable. In a single-star system like ours, planetary orbits are stable because the gravitational field has perfect spherical symmetry. The sun pulls equally in all directions at a given distance. But two stars create a lumpy gravitational landscape. Their combined pull shifts as they orbit each other. A planet doesn't feel a smooth, constant force. It feels a wobbling, pulsating tug that changes strength and direction on timescales of days or weeks. For decades, computer simulations said this wobble would accumulate, small perturbations would grow. Eventually, the planet's orbit would become so elongated that it would either crash into one star or get ejected entirely. The mathematics of three gravitating bodies, the famous three-body problem that Netflix's series dramatizes, seemed to forbid stable circumbinary planets. The simulations were missing something. What they underestimated was the self-correcting behavior of certain orbital configurations. When Kepler 16b was discovered, astronomers realized the planet sits in a gravitational sweet spot. Its orbital period is almost exactly 7 times the orbital period of its two suns around each other. This near resonance isn't coincidence, it's stability. When gravitational perturbations try to push the planet inward, the timing of its orbit relative to the star's positions creates counteracting nudges that push it back. The system self-corrects. It's like a ball that keeps rolling back to the bottom of a bowl no matter which way you tip it. Arrakis suddenly looked less impossible, but Dune's desert planet raises a second question, one the film visualizes with those endless dunes and precious water. Could a world orbiting two stars actually end up bone dry? The answer involves habitable zone geometry, and it's stranger than fiction. Around a single star, the habitable zone, where liquid water can exist on a planet's surface, forms a simple ring. Too close, water boils. Too far, it freezes. But around two stars, the habitable zone warps. Both stars contribute heat. Their combined luminosity determines the total energy reaching the planet. And because they orbit each other, that energy fluctuates. When the two stars in a binary system pass close together in their orbit, as seen from the planet, their combined brightness peaks. When they're on opposite sides, the planet receives light from two separated sources, which can actually change the day-night temperature patterns. Modeling this requires tracking two moving heat sources, each with its own spectrum and intensity. Dune's Arrakis has twin suns that appear relatively similar in the films, both producing harsh, bright daylight. The physics suggest this could happen if both stars are roughly sun-like, similar mass and temperature. Kepler 16, by contrast, has one star much dimmer than the other, a K-type dwarf and a red M dwarf. The planet there would see one dominant orange sun and a dimmer red companion. Not quite the Dune aesthetic. But here's the physical puzzle Dune glosses over. Arrakis is described as having had oceans in its past, before some catastrophe dried it out. The sandworms, we're told, are part of an ecological cycle that sequesters water. But could twin suns actually strip a planet of water more efficiently than a single star? Photodissociation might be the answer. Ultraviolet light from stars can split water molecules in a planet's upper atmosphere. The freed hydrogen, being light, escapes to space. Over billions of years, this process can drain a world of its oceans. Two stars means more ultraviolet radiation, potentially faster water loss, especially if one star is hotter and bluer than the other. Let's estimate the scale. Earth loses about 3 kilograms of hydrogen to space every second from water broken apart in the upper atmosphere. That sounds alarming, but run the numbers. 3 kilograms per second is about 95 million kilograms per year. Earth's oceans contain roughly 1.4 times 10 to the 21st kilograms of water. Dividing the ocean mass by the loss rate gives a depletion timescale of about 15 quadrillion years, thousands of times longer than the Sun's lifetime. Earth won't lose its oceans this way, but double the ultraviolet flux and halve the timescale. Put the planet slightly closer to the habitable zone's inner edge, and water loss accelerates further. Add a young, active binary pair emitting intense stellar flares, and you could plausibly strip a planet of its oceans in just a few billion years. Arrakis might actually make physical sense as an ancient ocean world that lost its water to aggressive twin suns. The James Webb Space Telescope is now testing ideas like this. Its instruments can detect water vapor, carbon dioxide, and other molecules in exoplanet atmospheres by watching how starlight filters through. In 2023, Webb observed the circumbinary planet Kepler 16b's system, not to study the planet directly. It's a gas giant, not a desert world, but to refine techniques for eventually finding rocky planets around binary stars. The search for Arrakis-like worlds is genuinely underway. But here's what Dune's physics gets subtly wrong. The stability sweet spot for circumbinary planets tends to place them at distances from their stars where temperatures favor gas giant formation, not rocky desert worlds. Kepler 16b is Saturn-sized. Most circumbinary planets discovered so far are similar, large, gassy, not terrestrial. For a rocky Arrakis to exist, it would need to form further out and migrate inward without being destroyed, or form from debris in a very specific orbital niche. Is that possible? Simulations now suggest, yes, barely. Certain binary configurations allow rocky planet formation in the habitable zone. The orbits must be just right. The stars must be neither too close together nor too far apart. The protoplanetary disk from which planets form must survive the gravitational churning long enough for rocky cores to coalesce. As of 2024, no confirmed rocky habitable zone planet around a binary star has been found. But absence of evidence is not evidence of absence. The detection methods favor large planets. Small rocky worlds are harder to spot. They're out there. The physics permits them. So when Paul Atreides watches twin suns descend behind Arraki's shield wall, he's looking at a world that gravitational chaos should have destroyed, baked by radiation that should have boiled its oceans away in an orbital configuration that computer models said couldn't last. And yet, the universe is stranger than models predict. Stars come in pairs more often than they come alone. Roughly half of all sun-like stars have companions. If even a small fraction of binaries host stable rocky planets, the galaxy contains billions of potential Arrakises. The sandworms are fiction. But twin suns over a desert world, physics says maybe. And maybe in astronomy is where discovery begins. Like if this was interesting, hit the subscribe for more and turn that notification bell on.